Imagine a kitchen run by the world's fastest super chef. They can chop, mix, and plate complex ingredients in a fraction of a second. But there is a serious flaw in the design of their restaurant. The massive pantry holding all the food is entirely in another room, and the ingredients can only be delivered to the chef through a tiny, agonizingly slow dumbwaiter. So what happens? The chef finishes prepping a dish instantly, and then they wait. They stand around doing absolutely nothing until the next single ingredient inches up the shaft. It doesn't matter if you have a chef who can process food at lightning speed. The restaurant's total output is entirely capped by the size of that delivery door. This kitchen bottleneck is the same engineering crisis unfolding inside the hardware that powers artificial intelligence. In this scenario, our hyper-fast super chef represents the AI processor. This is the compute, the physical hardware doing the actual mathematical thinking. The massive pantry where the food is stored is your memory capacity, holding all the AI's knowledge. And that tiny, slow dumbwaiter is your memory bandwidth, the physical pipes connecting the storage to the processor. For decades, the tech industry focused intensely on building smarter, faster brains. But they forgot to widen the pipes feeding those brains, creating a massive infrastructural choke point. To understand how we got here, we have to look at flops. Flops stands for floating point operations per second, a metric that measures how many mathematical calculations a processor can perform in a single second. This chart shows AI hardware growth since 2010. Processor speed grew at a staggering exponential rate, increasing 60,000 times. But looking at the blue line, we see the lag. Memory bandwidth has only grown 100-fold. This massive, expanding gap is known as the memory wall. Building a multi-million-dollar AI supercomputer today and hitting the memory wall is like buying a hypercar, but exclusively driving it in bumper-to-bumper city traffic. The memory wall went from a manageable nuisance to a critical emergency with the invention of large language models, or LLMs. LLMs are AI systems, like GPT-4, trained on massive amounts of text to understand and generate human-like language. Large language models are autoregressive. That means they generate text sequentially, producing just one single word at a time based on the words that came before it. To generate just one of those words, the processor has to reach into memory and scan billions of parameters. Parameters are the numerical variables that define the strengths of connections between different concepts the AI has learned. Because of this heavy lifting, generating text is what engineers call memory-bound. The processor spends the vast majority of its time sitting idle, waiting for parameter data to squeeze through the pipes. For conversational AI, having maximum raw computing power is effectively useless if the physical architecture cannot move the data fast enough to keep the processor fed. Let's go back to our restaurant. If you want to serve more meals, you don't spend billions training the chef to chop faster. You knock down the wall and build a massive cargo door. In hardware engineering, that bigger door is a technology called high bandwidth memory, or HBM. Instead of placing memory chips flat on a traditional motherboard, HBM architecture stacks them vertically into a dense 3D cube and places that cube directly on top of or right next to the AI processor itself. By placing the memory practically on top of the processor, you drastically reduce the distance data has to travel. You widen the dumbwaiter, allowing massive amounts of information to transfer simultaneously. HBM prioritizes data delivery over raw calculation speed. This transition shows that widening the pipe now yields a better return on investment than simply adding more compute cores to the brain. This hardware reality is actively changing how tech companies evaluate and purchase AI infrastructure. They are shifting their focus firmly away from peak flops. Instead, buyers are prioritizing holistic metrics like tokens per second. A token is the basic unit of text, usually a word or a part of a word, that an LLM processes. This metric tracks the entire system's real-world output. This chart tracking NVIDIA's GPU evolution reveals how the market is responding. Look at the transition from the H100 to the H200. The H200 achieves a massive performance leap solely through a memory bandwidth upgrade, while the red line representing compute power remains completely flat. The future of AI performance depends on whoever builds the widest pipes to feed the system, rather than whoever builds the biggest brain.